You can consider this video an introduction to related rates. I'm going to go pretty fast through this, so feel free to pause the video anytime you feel I'm getting ahead of you. So what I've included here are some general guidelines for working through one of these problems. The first one is to determine a working equation or formula. More on this when we get into some of these examples. Step 2 is to differentiate with respect to the proper variable. Since this is a rate, usually we're going to differentiate with respect to time. If you need more information on how to do that, look up implicit differentiation. There's plenty of videos on that. I have a YouTube video on implicit differentiation as well, so feel free to look that up if you're not sure what that means. And then what we're going to do after we've differentiated the formula or the equation, we're going to identify what we're looking for and then plug in the quantities that we have available to us. All right, on to the first example here. So we have a 15-foot ladder. It's leaning against a house and it's sliding down the wall. The question is asking how fast is the base of the ladder sliding across the ground when the ladder's 10 feet up the wall. Okay, so a quick little picture here. Let's make this our house. I'm not going to get creative or anything. We're just going to make that the wall of our house and this the ground. Okay, and then we have a ladder leaning against the house. All right, so determine the equation or formula. I see this right triangle here. So many times with a right triangle, you're going to use the Pythagorean theorem. That's what we're going to use here. Right triangle trigonometry could be used. Sometimes when you have similar triangles, proportions can be used. But here's what it says. It says keep variables as variables and constants as constants. So picture the situation in motion to help determine this. So picture this. As this ladder slides down the wall, you know, what else happens? The base of the ladder is going to have to move out. Okay, so look at the triangle. Do you see the sides that change? And do you see the side that does not change? Okay, so as this ladder moves out, this side length is getting longer, and as the ladder moves down the wall, this side length is getting shorter. So I've kept the variables, the things that vary, as variables. This ladder, though, it's 15 feet long. Okay, as it slides down, that's not going to change. So I see Pythagorean theorem here, and I'm going to write that out. A squared plus b squared equals c squared. All right, so that's part 1. Part 2 says differentiate with respect to t. So that's going to look like this. I'm going to differentiate the left-hand side by t, and I'm going to differentiate the right-hand side by t. So here we have 2x dx dt plus 2y dy dt. Derivative of a constant is 0. Don't be fooled by that. Don't try to use the power rule. All right. Determine what we're on step 3. Determine what we're trying to find here. And it says how fast is the base of the ladder moving out from the wall. So that's a rate. That's dx dt that we're going to look for. So that's that, which means we should be able to plug in something for x, something for y, and something for dy dt. So let's see what's given to us here. It's sliding down the wall at 2 feet per second. So dy dt, this is sliding down the wall at 2 feet per second. So not only is the rate 2, but this y value is getting smaller. So the rate is a negative rate. Let's see, the ladder is 10 feet up on the wall, so our y value is 10. And then our x value we still have to find here. And our x value, well, sometimes, you know, if we know that's 10 and that's 15, sometimes we have to go back to our original equation. If I plug in a 10 here and use the Pythagorean theorem, let's see, 225 minus 100 after I've squared that 10, square root of 125, I could write that there. I'm going to simplify that and write 5 radical 5. So as I simplify now, I get 10 radical 5 dx dt, and this is equal to 0, equals, add that 40 to both sides now, 40 And so dx dt is going to be 40 over 10 radical 5, or reduce here a little bit, 4 over radical 5, and our units are feet per second. Alright, so there's our first example. Next example. I've just recopied the guidelines up here so we can kind of look as we work through this problem. Alright, so we have a particle that's moving along this function y equals x cubed. It says determine how quickly the particle's distance to the origin. So let's look at the distance to the origin. So this point is going to be moving around here, back and forth, okay? And we need to determine how quickly this is changing. So in our differentiated equation, it's going to be dd dt that we're looking for. All right, so you might think that this is our starting equation, but this has nothing to do with the distance. It has to do with the coordinates of this function, the solutions of this function. We need to talk about this. So as I look here, and this is another Pythagorean theorem problem. So we have our, how do we get to this point, xy? We move in an x direction and a y direction. Let's see if I can plug in any of these numbers before we start working here. What's a constant? What's a variable? Let's see. As this slides up, I see this triangle, all three sides change. So as this moves up, I see the y value gets bigger, I see the x value gets bigger, and I see that that distance d also gets bigger. So as I write this out here, I have the Pythagorean theorem. All right, differentiate everything with respect to t. I know I'm going to have to write smaller here too. So when I do that, I get 2x dx dt plus 2y dy dt equals 2d dd dt. And you don't have to do this next step. I like to do it because it reduces this equation a little bit. Divide both sides by 2 and we have this. X dx dt plus y dy dt equals d dd dt. Okay, so earlier we said we need to figure out how quickly the distance to the origin is changing. That is this quantity right here. That means we should be able to plug in values for all 5 of those unknowns. All right, so it says it's at the point 2, 8. So x is 2, y is 8. Let's do that. So x is 2, y is 8. Let's see. The x-coordinate is increasing at 3 units per second. So the x-coordinate, dx dt, is changing at 3 units per second. It says it's increasing. So that's going to be a positive value. Let's see, dy dt, they don't give us that. D, they don't give us that, but we can find it here in a second. Let's see. Once again, if we know x is 2 and y is 8, we can use our Pythagorean theorem to get our distance here. So that squared plus that squared, 64 and 4 is 68. So the square root of 68, that's going to be 2 radical 17. All right, dy dt. So you might have thought, all right, they don't give us dy dt, but here's this equation that relates x and y. If we differentiate that with respect to t, this gives us a relationship between dx dt and dy dt. This is what we're looking for now. So let's see, dy dt is 3 times our x value squared, so 2 squared. And dx dt they give us is positive 3. So let's see, we have 36 here. dy dt is 36. So we come back up here, here's our 36. Okay, so continuing this equation down here, a little simplification. Let's see, we have 2 radical 17 dd dt. And we have 36, 72, 288 plus 6. 288 plus 6, 294. So 294 equals 2 radical 17. Divide both sides by 2 radical 17 and we get dd dt equals 294 over 2 radical 17. And we could reduce it. I'm going to be lazy right now and not do that, but I'm going to leave my answer as, let's see, units per second. And there's our answer for that. Maybe, sorry to be lazy. Let's do it. What's that going to be? 147 over radical 17 units per second. I don't want to be lazy. All right, there's our answer. Introduction to related rates.